Welcome back, AP Calc BC students, to our final video covering topic 10.4, the integral test. Maybe not one of our favorite tests so far, but it is a test that can bail us out if we find that a lot of the tests that we already know or will soon know don't seem to do the job for us. So we're going to take a look at our third example here from example 1, part C. Confirm whether the integral test can be applied, and then use it to determine the convergence or divergence. If you remember, so far we're one of two, right? We're 1 and 1. Part A did converge. Part B, we actually, well, we never had a chance to really use the integral test in part B because the conditions weren't met. So let's see what happens with this particular problem. So the very first thing that we're going to have to do is revisit our idea of the integral test, which says that we have to have a function that's positive, continuous, and decreasing for some x that's greater than m. Now, let's take care of that before we dive into this part, because again, we might be wasting our time if we integrate this problem. So very first thing that I am going to do is check whether or not I can let some function f of x be my a sub n, and we can always do that. That's never a problem. So that basically is going to say that from this point forth, f of x is going to be 1 over x squared plus 1. And again, if you're wondering why we do that, it just simply allows us to do a lot more calculus stuff, right? We can do more calculus stuff with a function than we can with, say, a discrete set of points. But yet, we have determined that the same conclusions can apply for both. So, number one, is this function f of x positive? Well, I don't think it takes a whole lot of intuition to figure out that this is true. Doesn't matter what x you plug in. In fact, if a student were to just say f of x is positive and stop, I'd be okay with it because it's not a false statement. A stronger argument would be to say for what values of x that were positive that are pertinent to the question, and since n starts at 1, we can start our x at 1. Number two, what about continuity? Well, if you look at this denominator, there's nothing that's going to stop that denominator from being anything that can be defined. In other words, you're not going to get a 0 anyway from that denominator. You're not going to get strange things that we just aren't allowed to have. So f of x is continuous all the time, but moreover for us, we can be a little bit more thorough and say x greater than or equal to 1. All right, well, the very next thing that we need to do is talk about the increasing, decreasing nature. We want this function to be decreasing, and this is where you're going to earn your money, right? You guys get paid for doing math? Yeah, me neither. So we're going to go ahead and change this to x squared plus 1 to the negative 1 power. Okay, make our job a little bit easier, and let's take this derivative. Okay, well, this derivative is going to be negative 1 quantity x squared plus 1 to the negative 2 power, and then we multiply by the 2x, and then if we simplify, we get negative 2x on top, x squared plus 1 squared on the bottom, and I think it's probably pretty clear to you. Critical numbers are going to be 0 from the top, which doesn't even come into play. And then if we just test along the interval from 1 to infinity, something like, I don't know, 2 sounds good to me, f prime of 2 is going to be negative 4 over 5 squared, and I'm quite sure that that's negative. And so I feel quite sure that f of x is decreasing. And we could say decreasing on the interval 1 to infinity, or we could say decreasing for x greater than or equal to 1. So there we go. All three boxes are checked. The integral test applies, which means we just got a little bit more work to do. So basically, we now want to find this value of the improper integral, or not so much the value of it. We just want to find out what the behavior is. And we know that whatever that improper integral does is what our series will do, converge or diverge. So how to set this up? Well, you're going to rewrite this as the limit, or as the integral, sorry, from 1 to infinity of 1 over x squared plus 1 with respect to x. Now, you all know that that's not a great way to introduce an improper integral because the fundamental theorem of calculus doesn't play very nicely whenever you have infinite boundaries. So we'll fix that and let x, sorry, I'll get it right, guys. We'll let some arbitrary constant approach infinity. If you've been with me all year, you pretty much know that I like to use b to replace my upper boundaries. I'll use something like a to replace the lower boundaries. But by and large, you can pick any variable you want as long as you stay away from x. All right, now we need to integrate 1 over x squared plus 1. Hopefully you all realize that is the inverse tangent. So our limit drops down. We've got our good friend, the inverse tangent, that will be evaluated from b to 1. And if we make that happen, our limit is now going to act upon the arctangent of b minus the arctangent of 1. Kind of ran into my box there. So if we let b become infinity, and we've had this conversation a little bit in the past, is if you think about the graph of arctangent, not a graph that you see all the time, but it looks a little something like this. And this graph has this very neat feature in that it has this horizontal asymptote right there at pi over 2. If you think about the vertical asymptote that exists for tangent at pi over 2, why wouldn't it be a horizontal asymptote at that same location for the inverse tangent? So when you let b get really big, you end up with a pi over 2 here. And then the arctangent of 1 is just a constant that we can compute. And basically that's a 45-degree angle that gives you the ratio of tangent ratio of 1 over 1. And so pi over 2 minus pi over 4 is indeed pi over 4. Last time I checked, that is a finite number, which means that our integration, our definite integral, converges. So if the definite integral, the proper integral converges, therefore we can conclude that our series, summation as n goes from 1 to infinity of 1 over n squared plus 1, converges as well. Now, before we say goodbye, let's make sure that we get something straight here. By no means does this summation converge to pi over 4. It does not add up to pi over 4. So we can't use that, right? Honestly, I couldn't tell you what this adds up to, and we really don't care at this point. We just want to know whether or not it does add up to something or not. So don't confuse the answer for your improper integral to what the sum is, because very, very rarely, if ever, is that going to be the case. That wraps up our 10.4. Stick around. 10.5 P-series and harmonic series will be coming your way. As always, thanks for joining.